Chapter number 5 of the textbook of Mechanics of Materials is about analysis and design of beams for bending. Before this chapter, we have discussed pure bending in chapter number 4, where we derived an expression for the normal stress, which was sigma is normal stress, it is equal to mc over I. This is for maximum bending. Here the maximum value was at the outer surface of the beam, which has maximum distance from neutral axis. This distance was c. So this normal stress, we used to calculate this normal stress from the cross section of the beam and the given value of bending moment m. If we know the value of m, we can find c, which is distance from neutral axis to the outer surface of the beam, and I is moment of inertia of the cross section. This was maximum stress for any given value of m. Here m was either given in the problem, or if we know m will be a single value. In this chapter, m was a single value. But then in this chapter number 5, we will now study that along the length of the beam, bending moment may vary. Whatever the transverse load is, either it can be a concentrated load, or it can be distributed load. It can be a combination of concentrated and distributed loads or moment. So bending moment will be different at each point between A and B. It will be different between A and C. At every point between A and C, C and D, D and E, E and B. So bending moment will be a function of length. X is length. So there will be a variation in the values of bending moment. It can be minimum at some point and it will be maximum at some other point. So the maximum value of bending moment is important for us. If we put maximum value of bending moment in the expression above, maximum absolute value, it can be either negative or positive. We will just take the positive magnitude of it. Negative or positive means sense of the moment. It can be counterclockwise or clockwise. So now in this chapter, we will use the same formula for maximum normal stress, but in this case, we need maximum moment along the length of the beam, because moment is a function of length of the beam. It is also a function of load. So we will, for each and every beam in this chapter, we will calculate moment as a function of length and load, and we will draw bending moment diagram along the length of the beam. On the horizontal axis we will have length, and on the vertical axis we will have bending moment, and from that bending moment the maximum value will be important for us, which we can use in the expression to calculate maximum normal stress in the beam or bending stress in the beam. Similarly, we will also draw another diagram in this chapter, which will be shear force diagram. It will be drawn before the bending moment actually. I am discussing it after bending moment because you earlier you are familiar with the normal stress. So bending moment is important to calculate normal stress, but we will calculate shear force V. V is shear force, and from the shear force we can calculate shear stress in the beam, which we will do in chapter number 6. In the current chapter, we will just calculate shear forces and bending moment in the beam as a function of its length and load, and we will draw the bending moment and shear force diagrams along the length of the beam. This is a very important chapter, and there are some important concepts being discussed in this chapter. This chapter is directly linked to chapter number 9 of the book, which we will study later in Mechanics of Materials 2 course. The shear force diagram and the bending moment diagram. Similarly, functions of shear force and bending moment are very important for us for chapter number 9, which will be used to calculate slope and deflection of the beam at various points in chapter number 9. So focus on this chapter, learn how to draw shear force diagram and how to draw bending moment diagram, how to write a function of shear force for a beam and function of shear force for the function of bending moment for a beam. Objective of this chapter is to analyze and design beams. So we will analyze and design beams in this chapter. How to analyze? We can calculate shear forces and bending moments at different locations, at different points on the beam. If we have a function of shear force or bending moment as a function of length, so whatever value of length we put in the function, we can calculate shear force and bending moment from the function. Similarly, on the basis of those maximum values of bending moment and shear forces, we can design beams or desired beams for different applications. What is beam? Beam is a structural member supporting transverse loads at various points along the member. In the diagram, you can see there is a member and there are some loads perpendicular to the axis of the member of the beam. These perpendicular loads, perpendicular to the axis of the beam loads, are actually transverse loads. Transverse loadings of beams are classified as concentrated or distributed loads. So transverse load can be concentrated like P1 and P2, and that can be distributed load like W in this case. The distribution can be uniform distribution, or it can be linear distribution, parabolic distribution, or random distribution. Applied loads result in internal forces consisting of a shear force from the shear stress distribution and a bending couple from the normal stress distribution. Earlier in chapter number 4, we have already discussed that transverse forces cause internal forces in members equivalent to shear force and a couple. So wherever we, for example, at section C, we want to find internal reactions in the beam. So those internal reactions will consist of a shear force V and a couple M. So this shear force is responsible to produce shear stress, and bending moment produces normal stress. Normal stress is often the critical design criteria for the beams. So we have derived this expression in chapter number 4, My over I, normal stress in the beam, where y is the distance of any point from the neutral axis, vertical distance of any point from the neutral axis. And if that distance is equal to c, it is maximum distance, so it will be maximum stress. Or we can write it as m divided by I over c. I over c is actually section modulus. M over s can be written as m over s. S is section modulus. Here, if we use the maximum value of moment, we can find maximum value of stress in the beam. Okay, so now we will require to determine the location of maximum moment and magnitude of the maximum bending moment. Okay, here are some types of beam supports. If the number of supports if the number of unknown reaction forces, each support produces some reaction forces in the beam. If we draw a free body diagram of each beam, the reactions are replaced with unknown reaction. The reactions are replaced with unknown reaction forces, just like a pin reaction is replaced with two forces in x and y direction. Similarly, a roller support is replaced with a normal force, a normal reaction force. So if the number of reaction forces in a beam are more than number of the equilibrium equations to solve or to calculate those unknown reaction forces, the beam is called statically indeterminate beam. And if we can use equations of equilibrium to calculate all the unknown reaction forces in a beam, such kind of beams are called statically indeterminate beams. In 2 dimensions, we have 3 equilibrium equations. Summation of fx is equal to 0, summation of fy is equal to 0, and summation of moment is equal to 0. Currently, we are studying about, we are studying only 2-dimensional problems. So here are some beams, like the simply supported beam. It has 3 unknown reactions, 2 at the pin support and 1 at the roller support. So total 3 number of unknown reactions can be calculated from 3 equilibrium equations. Similarly, for an overhanging beam, there are 2 reaction forces at the pin support and 1 reaction force at the roller support. Again, 3 number of unknowns can be calculated from 3 equations of equilibrium. For a cantilever beam, there are two reaction forces and one moment, total 3 number of unknown, and we can find them using 3 equations of equilibrium. But there are some statically indeterminate beams where number of unknowns will be more than number of equilibrium equations. For example, this continuous beam has one pin reaction, so pin support offers 2 reaction forces, then there are more than one roller supports. It can be 2, 3 or 4, more than one roller supports. So the number of reaction forces in this beam are 4. If we increase the roller supports, the number of unknowns will increase. So the number of unknowns in this case are 4, which are more than the number of equations, and it is statically indeterminate beam. Similarly, the beam fixed at one end and simply supported at the other end. So at the fixed end, we have 3 unknown reactions, 2 forces and 1 moment. And at the roller support, we have a reaction force, total 4 number of unknown reactions, which are more than number of equilibrium equations. A fixed beam has both ends fixed, and both ends have 3 unknown reactions, 2 forces and 1 moment at each end. So there are total 6 number of unknowns, which are more than number of equations, and this beam cannot be solved using equations of equilibrium. This is statically indeterminate beam. So in this chapter, we will discuss about statically determinate beams only, and in chapter number 9, I will discuss, or we will learn how to solve statically indeterminate beams as well. Currently, we will discuss statically determinate beams only in this chapter. Okay. Shear and bending moment diagram. Shear force and bending moment diagram. Determination of maximum normal and shearing stresses require identification of maximum internal shear force and bending couple. Just like I have discussed earlier, for normal stress, we need to calculate maximum bending moment. And for shear stress, we need to know shear force. So how to know shear force and shear bending moment? Shear force and bending couple at a point are determined by passing a section through the beam and applying an equilibrium analysis on the beam portion on either side of the section. For example, in the given diagram, if we want to find shear force and bending moment at point C, we will pass a section from point C. We will cut the beam into 2 sections. There is a right side section and a left side section. They are given here. At the common point where the beam has been sectioned, on the right and the left, there will be shear force and bending moment. Those shear forces and bending moments will be equal and opposite because they both are existing at the same surface. Either this surface in the left side and this surface in the right side, they both are common. They are part of the same beam. So shear force will be same, direction will be opposite. In the upper diagram, where the left side has been considered, shear force has been denoted as downward and bending moment has been denoted as counterclockwise. In the bottom diagram, where right side of the beam has been considered, shear force is denoted with the upward direction and bending moment with a clockwise direction. This is sign convention. Throughout this chapter, we will use this sign convention. Whenever we cut a beam, section a beam at any point to find shear force and bending moment, we will consider either the left side or the right side. You can consider either this one or this one. Any one, we can find shear force and bending moment. They are same in both the sections. So if we are considering left section, we will use this convention, downward shear force and counterclockwise bending moment. If we are considering the right side, we will denote shear force with an upward direction and bending moment with clockwise sense. This is sign convention. We will use it throughout this book, this study of mechanics of material. So remember this sign convention. If our supposition is wrong, for example, if we consider left side and denote shear force with a downward direction, if we are wrong, the value we calculate will be negative. Similarly, if bending moment is against our supposition, if it is clockwise in this case, so whenever we calculate it, it will be negative. But initially we will use this convention. Okay. Here's a sample problem 5.1, and we will know how to calculate shear forces and bending moment in this beam, given in this beam. For the timber beam and loading shown, draw the shear and bending moment diagrams and determine the maximum normal stress due to bending. First, we will draw shear force and bending moment diagrams. In these diagrams, as discussed earlier, the horizontal axis will be length, and the vertical axis in one of the diagram will be shear force, and in the other diagram it will be bending moment. After that, we will find maximum normal stress. So once we draw the bending moment diagram, we will find maximum moment, and from the maximum moment, dividing it by section modulus, which we can find from the cross section of the beam, we can find maximum normal stress which is required. Okay. Now, if we do not know where the moment is maximum or where the shear force is maximum, we have to draw the diagrams. To draw the diagrams, we need to know shear force and bending moment at each and every point on the beam. For that, we have to section the beam between each two forces. Remember this method. In order to find shear force and bending moment in a beam, or shear force and bending moment diagram in a beam, we have to section the beam between each two concentrated forces, between each two moments, between each force and moment, between each concentrated force and distributed force, and similarly between somewhere between starting point and ending point of a distributed load. If there is a distributed load, which will come in the next problem, we will section the beam between starting and ending point of the distributed load as well. For example, if we section this beam between point A and point B, because at point B there will be a reaction force, similarly at point D there will be reaction force. So we have to section this beam between A and B, and we do not know this length. We will call it X, and this X will vary between 0 and 2.5 meters. Okay, one of the method is this one, but I do not want to use this method in this problem. We will use it in the next sample problem. Currently, I do not want to introduce a variable here, X. I want to section this beam right after point A, section number 1. This section number 1 is on the right side of point A, and it is so near to point A that it has 0 distance from A. Okay, then the next section is at B, on the left side of the B, and it is so near to B that this section number 2 has 0 distance from point B. It has distance of 2.5 from point A. The third section will be on the right side of the beam, on the right side of the point B, section 3. Again, section 3 is on the right side of the B, and it is so near to B that it has 0 distance from point B, and it has 2.5 meter distance from point A. Section 2 and section 3 there's a difference between 2 and 3. 2 and 3 both are almost at B, but 2 lies slightly on the left side of the B, and 3 lies slightly on the right side of the B. They both have 0 distance from point B. But if we section the beam at 2 and we consider the left side, there is no reaction force on the left side of section 2. It is on the right of the section 2. But if we consider it as section, okay, here will be shear force and bending moment, which are unknown. But if we consider section 3, again it is of the same length. But on the left of section 3, there is a reaction force RB. So this is the difference between section 2 and section 3. RB force, if we draw the left side of the beam, the force RB is not included if we section the beam at point 2 or at section 2, and it will be included if we section it at 3. So we will, okay, this method can be used if we have all concentrated loads on the beam, if there is a distributed load, then there will be variable shear force and variable bending moment between the 2 points, starting and ending point of the distributed load. So we will not prefer this method for distributed loads. Currently in this problem, we have only concentrated loads, so I want to use this method. Again, the next load is at point C. So one section immediately at the left and the other at the right of the section C. And the last one at point D, we have a load which is reaction force RD. So we will section it at immediate left of point D, which has zero distance from point D, but there is no right side of point D. And there is nothing on the right side of point D. The beam ends here, so we have no section on the right side of the point D. Just like we have no section on the left of point A, because the beam starts at A. There is nothing at the left of point A. Okay, before everything, we have to calculate two reaction forces, RB and RD. These two reaction forces can be calculated from equations of equilibrium. First, you will take summation of moments at point B is equal to 0, so you can find RD. And then summation of moments at point D is equal to 0, so you can find RB. Or you can even take summation of forces in y direction is equal to 0. So this is your assignment to find RB and RD. This is part of engineering statics and I will not repeat it here. We have calculated it here. Summation of forces is equal to 0 and summation of moment equal to 0. So the numerical values are shared here with you. RB is 46 kilonewton and RD is 14 kilonewtons. You must know how to calculate reaction forces using free body diagram. This is part of the problem, but you have already learned it in engineering statics. So I assume that you must know these calculations or this method, how to calculate reaction forces. If you do not know how to calculate reaction forces, this is first step of the problem. Every problem in the engineering mechanics of materials, the first part of every problem is to calculate reaction forces from a free body diagram. So you must know this. If you do not know, you cannot solve numerical problems of mechanics of materials. Okay, RB is 46 kilonewton, RD is 14 kilonewton. You have to do it by yourself, 46 and 14. We have sectioned the beam just like I discussed earlier at point 1, 2, 3, 4, 5, 6. 1 is at immediate left of point A. It is assumed to have zero distance from point A. So when we section the beam at 1, here's its free body diagram. We are considering left side of the beam only. Remember that throughout this chapter, mostly I will consider the authors of the book also. They are considering the left side of the beam after sectioning. You can consider the right side as well. Just the sign convention of shear force and bending moment will change. There will be nothing changed in the results. Okay. No difference will be there in the results. So we have sectioned it at point 1 and there is a downward force V1 and counterclockwise moment M1. The length of this section is 0, almost 0, because we have considered that section 1 is so near to point A that it has no distance from point A. If it has no distance from point A, then it is almost at point A. To calculate shear force, we can use summation of forces is equal to 0, the equation of equilibrium. Summation of forces in vertical direction is equal to 0. So there are two forces only, V1 plus 20. Both are in the same direction, so I'm using positive sign for both of them. In this case, I'm using positive sign for downward forces. So V1 becomes minus 20 kilonewton. Okay. Now, summation of moments is equal to 0. We will take summation of moments at this section equal to 0. So here, if I consider counterclockwise moments positive, there is one moment M1. Then there is force V1. V1 is acting on the same surface where we are calculating moment. So V1 has no effect, no moment here because it has zero distance from this surface. So V1 is producing no moment. Similarly, 20 kilonewton force is producing a moment in the same direction, but it has zero distance from the surface because we are considering that surface 1 is almost at point A. It has zero distance from point A. So M1 becomes 0. Similarly, After sectioning the beam at surface 2, here, if we draw the shear force diagram, if we draw the free body diagram here, everything on the left side of the section 2 has been drawn. This force 46 kilonewtons is on the right side, so it is not included here, although section 2 is almost at point B. Okay, it has the distance 2.5 from end A because it is almost at point B. So this distance, this length is 2.5 meters. Summation of forces in vertical direction is equal to 0. Again, V2 plus 20 is equal to 0. So V2 becomes minus 20 kilonewtons. And summation of moments is equal to 0. If I consider counterclockwise moments counterclockwise moments as positive. So here one moment is M2. The force V2 is not producing any moment at the section 2 because it is along the section 2. It has 0 distance from section 2. But in this case, the 20 kilonewton force is also producing a counterclockwise moment, and it has a distance of 2.5 from the end. So M2 will be equal to minus 50 kilonewton meters. Okay. Then if we section the beam at point 3, which is almost at point B, but on the right side of the point B, now we have to include this force of 46 kilonewton because it is on the right side of section 3. So here is section number 3, where there is a 46 kilonewton force at section 3 and a 20 kilonewton force at point A. Now summation of forces is equal to 0 in the vertical direction. This length is also 2.5 meters. So here there is a force V3 downward. I am considering downward forces as positive. Then a 20 kilonewton force downward is again positive, and then a 46 kilonewton force upward. Upward is denoted with negative sign because I have considered downward forces as positive. So V3 will be plus 26 kilonewtons. Similarly, summation of moments is equal to 0 if I consider counterclockwise moments equal to as positive. So M3 is counterclockwise. V3 is not producing any moment. It is on the same point where we are calculating moment. Similarly, 46 kilonewton force is on the same point. It is on point B, and section 3 is also at point B. Immediate right of point B, we are considering 0 distance between 3 and B. So this 46 kilonewton force is also at the same point. It has 0 distance, so it is not producing any moment. And then 20 kilonewton force has a distance of 2.5. So M3 is again minus 50 kilonewton. Similarly, if we section the beam at 4, 5 and 6 and we draw the free body diagrams in the same fashion, we have V4, M4, V5, M5, V6 and M6. Similarly, you can use summation of forces equal to 0 to find forces V4, V5 and V6, and summation of moments to find moments M4, M5 and M6. So here everything has been done. You can see the calculations. V1 is minus 20 kilonewton, M1 is 0, V2 is minus 20 kilonewton, M2 is minus 50, V3 is 26 kilonewton, M3 is minus 50, V4, V5, V6, M4, M5 and M6. All the numerical values are given to us. Now we can draw the diagrams. Okay, here we have the beam. Whenever we draw the diagrams, shear force and bending moment diagram, always remember to draw them below the beam. First draw the beam, the free body diagram of the beam, and then below the beam draw the shear force diagram and then the bending moment diagram. You can compare it with the beam. At point A, this section 1. Point B, we have section 2 and 3. Point C, we have sections 4 and 5. And at point D, we have section 6. So at point A, at section 1, we had shear force You have to draw it on graph paper, or if you are drawing it on a plain paper, you have to use proper scale. You have to draw it neat and clean. Otherwise, there will be errors and it will not be acceptable to most of the examiners or reviewers. Okay. At point 1, we calculated V1, which was minus 20 kilonewton. At point 2 again, our calculations told us that V2 was minus 20 kilonewton. This is V2. So minus 20 and minus 20, we have to draw them. We have to join them. They're constant. The shear force is constant between 1 and 2. Again, at 3, we calculated shear force equal to V6, 26. V3 equal to 26. It is here. V3, sorry. V3 is here. It is 26 kilonewton. V2 and V3 both lie at point B. 2 is on immediate left of B and 3 is on immediate right of B, but they both are almost at B. So at B we have two forces, shear forces, V3 and V2. So there will be a vertical line between these two because they both exist at the same point B. Okay. Then at section 4 we had the same value, 26 kilonewton. So there will be a constant line between B and C, 3 and 4. At 5 again, 4 and 5 both sections lie at point C. So at 4 it is 26 kilonewton, at 5 it was calculated as minus 14 kilonewton. So these two values exist at the same point C. So there will be a vertical line. And finally, at point 6, which is at point D, section 6, which is at point D, again, it is minus 14. So it will remain constant between 5 and 6, or C and D. So this is shear force diagram from starting end of the beam, end A to end D. We have drawn shear force diagram as a function of length of the beam. Now we will draw the bending moment. We have already calculated bending moments as well at all the points 1, 2, 3, 4, 5 and 6. So at point 1 or at section 1, we calculated bending moment is equal to 0. You can see those numerical values on our previous slide. At section 2, which is at point B, bending moment was M2 was minus 50, and section 3 also again it was minus 50. Let us see it here. M2 and M3 both have same value of bending moment. Similarly, M4 and M5 have same values. So at 3 and 4, which are both both exist at point B, section 2 and section 3 both exist at point B and both have same value. M2 and M3 both have same value, minus 50. So we have to draw this point 1 or point A with, we have to connect point A with point B, and we will connect it with a linear line. Why we have connected them with a linear line? Why not with a curve, a parabolic or a cubical curve? Remember that we will discuss the reason, or we will derive it later, but currently just know the fact that if shear force is constant between 2 points, bending moment will be linear. If shear force is linear between 2 points, bending moment between the same 2 points will be parabolic. If shear force is parabolic between 2 points, bending moment between the same 2 points will be cubical. So bending moment is always 1 degree higher than the shear force. Similarly, shear force is always 1 degree higher than the load. If load is constant, shear force will be linear between 2 points. If load is linear between 2 points, shear force will be parabolic. And if load is concentrated load, if there are two concentrated loads at two different points, shear force between them will be constant. So we can see that there are two concentrated forces at A and B, so shear force is constant between A and B. Similarly, between B and C, it is constant. Between C and D, it is constant, because all these points, there are concentrated forces at these points. Okay, coming back to the point, M3 and M4, section 3 and 4 both lie at point B, and we have minus 50 kilonewton meter. We have drawn a linear line because between A and B, because shear force was constant between A and B, so bending moment should be 1 degree higher, it should be linear. Okay, at point C, section 4 and 5, we have M4 and M5 both equal to 28 kilonewton meter. So again, shear force is constant between point B and C. So we will draw a bending moment as a linear line between B and C. And bending moment at 6, which is at point D, was 0. We calculated it already. So again, there is a constant shear force between point C and point D, here this one. So bending moment will be linear. So we have drawn a linear line. Okay, both the diagrams, shear force and bending moment diagrams have been drawn. Now we need maximum value of bending moment. The maximum value of bending moment from this diagram can be seen. It is minus 50 kilonewton meter. Remember that we have to consider the magnitude only, not the negative or positive sign. Signs show direction only. So the absolute value, absolute maximum value is minus 50 kilonewton. So maximum moment is 50 kilonewton meter. Negative sign is not important for us. So maximum moment is MB, which is 50 kilonewton meter. Maximum shear force is 26 kilonewton, but it is not important for us in this problem. Specifically, we are not asked to find shear stress. So shear force is not important. Okay. First part of the problem was to draw the shear force and bending moment diagrams, and we have drawn them. Second part was to find maximum normal stress. So it will be maximum moment divided by section modulus. Section modulus for a rectangular shape beam, rectangular cross section beam, here it is rectangular. So for rectangular beams it is 1 over 6 BH square, or 1 over 6 AH. A is area, B is width, H is height. H is 250 mm and B is 80 mm. So we can simply calculate shear section modulus. It is equal to 1 over 6 BH square. So we have converted width and height into meters. Section modulus becomes 833.33 into 10 power minus 6 meter cube. Okay, now we can put the values here. Maximum moment, which has been calculated already, it is 50 kilonewton meters, 15 to 10 power 3 newton meters, divided by section modulus, which is 833.3 into 10 power minus 6 meters square. So maximum stress becomes 60 into 10 power 6 pascals, or you can write it as 60 megapascals. 10 power 6 is equal to mega. So it was very simple. First we have drawn shear force and bending moment diagrams, which was required in the problem. We sectioned the beam at different points at the right and left side of each force in the beam, because all the forces were concentrated. And then we have calculated shear force and bending moment at all the section points, and then we have denoted the numerical values on a graph paper, and we connected the points between concentrated forces. The points are connected and with a line, and it will be constant shear force always. And for bending moment, it is always 1 degree higher than shear force. So whenever we connect 2 points, we have to see if the shear force diagram was the constant, or it was linear, or it was parabolic. So bending moment will be 1 degree higher than the shear force. Okay, and then we calculated maximum stress from this expression, because we know maximum moment from the bending moment diagram, and section modulus can be calculated from its expression. So maximum stress has been calculated as 60 megapascal. Okay, we will move towards the next sample problem, which is sample problem 5.2. In this problem, we have been given a distributed load of 3 kilopounds per feet between point A and C. Similarly, a load at point E, 10 kilopounds load at point E will produce a moment at point D. If we shift this load from E to D, we have to draw a free body diagram here. So if we shift the force from E to D, we have to replace it with a force couple system, it is 10 kilopounds. You already know that if we have to shift force from a point to another point, if the 2 points are not in the same line of friction, we can replace the same force at other point with the same force and a couple. This force is producing a moment of 10 into 2 feet. Between E and D there is a 2 feet distance. So 10 into 2 becomes 20 kilopounds feet moment. So we can simply cross this force from here. Okay, and then there are reaction forces at point B. Those are unknown. By, Bx, and moment. Or we can call it Rb, By or Rb, whatever. Okay, the structure shown is constructed of a W10 cross 112 rolled steel beam. So this W10 into 112 is a wide flange beam, and we can get data for this beam from the end of the book, from appendix C, if you want to know the section modulus S or the moment of inertia I, or if we want to find C, we can find it from the table, from the appendix. All the data is given in the appendix for the standard beams. Appendix C. Okay, draw the shear force and bending moment diagrams for the beam and the loading given. So similar to the previous problem, we will draw shear force and bending moment diagram, but here I will use a little bit different method. So you will learn it. It is a very important one. Determine the normal stress in the sections just to the left and just to the right and left of point D. So to the left and to the right of the point D, we have to find maximum stress, normal stress. Sorry, not maximum, normal stress. So normal stress is equal to moment divided by shear force. So at point D, we will find moment. They are not asking about maximum normal stress. They are asking normal stress at the left and right. So at the left of point D, we will find moment, and then at the right of point D, we will find moment. And by putting it in this expression, we can find maximum normal stress to the left and right of the section D. Okay, first we will find the unknown reaction forces at point B. You can find it by yourself using laws of equilibrium, equations of equilibrium, and it is very easy. Simply, we have two unknown forces. Using equations of equilibrium, you can find them. Those are 34 kilopounds and 318 kilopound feet. This is your assignment. You can do it by yourself. If you understand engineering statics, you can apply equations of equilibrium to these to calculate the unknown reaction forces here. Okay, as discussed earlier, I told you that if there is a distributed load, we have to section the beam between starting and ending point of the distributed load. So here there is a distributed load between point A and C. So I will section the beam. The first section, we are starting from the left hand. The first section will be between A and C. Now I am not just sectioning the beam to the immediate right and left of every point. Now I will use a variable x here. This x starts from A and it ends at C. So x is between 0 and 8 feet. This is our section number 1. The section 2 will be between point C and point D, because the next force and our moment changes at point D. After D, the next change is at point B, so we will produce a section between D and B. So totally we will produce 3 sections, 1, 2 and 3, and for each section we will consider a variable x, and x will be starting from end A to the distance up to the distance until the point where we are ending the section. Okay. Here we have produced section 1 between point A and C, section 2 between C and D, and section 3 between D and B. If you draw the free body diagram, after sectioning the beam at 1, the left side of the beam has been drawn here. There is a downward shear force and counterclockwise moment. The length of the segment is x, and the x varies between 0 and 8 feet. The force, this distributed force is 3 kilopounds per feet. So if we want to convert into concentrated force, initially we will convert into concentrated force to find V, because V is also a concentrated force. We can only add or subtract two concentrated forces. We cannot add a concentrated force with a distributed force. So to find V, we have to use summation of forces equal to 0. For that equation, we need a concentrated force, not a distributed force. So this 3 kilopounds feet, 3 kilopounds per feet force, per foot force can be calculated, can be converted into a concentrated force by simply multiplying it with the length. In this case, length is x, so it becomes 3x. And as per our understanding, this force acts at the centroid of the load, and it is a rectangular load. The centroid will be at the geometric center. It is mid of it. X, if the total length is x, so the half is x by 2. Summation of forces is equal to 0 in y direction. So V plus 3x is equal to 0. So V becomes minus 3x. So here V is a function of x. It is a linear function of x. So remember that shear force diagram will be a linear line because it is a linear function of length. Summation of moments is equal to 0. Let me consider counterclockwise moments equal to 0. So M is here. This force V is not producing any moment at section 1. So we are not considering it. This 3x force will produce moment in the same direction as M. So I will use positive sign. 3x into its distance. The distance is x by 2. So M becomes minus 3 by 2 x square, or minus 1 by 1.5 x square. Okay, so M is 1 degree higher than the shear force. M is a quadratic function of length x, and shear force is a linear function of length x. Again, if we section the beam at 2 and then consider the left side of the beam after sectioning it from here up till point A, the left side of the beam, there will be a shear force downward at section 2, a bending moment counterclockwise. Total length of the beam is x. This length is known to us, length of the distributed portion, because now it is a total distributed load. We know it from start to the end point. It was 8 feet in the given diagram. It was 8 feet. So this is known to us. It is 8 feet. Okay, if it is 8 feet and 3 kilopounds per feet means 8 into 3, 24 kilopounds concentrated load. And this concentrated load will act at the midpoint, which is 8 by 2. So it becomes 4 feet from this end. If the total length is x, the distance of this 24 kilopounds force is 4 feet from the left. So it has x minus 4 feet distance from the right end, from section 2. Now again, we will use summation of forces in y direction is equal to 0. So we have force V downward. If I am considering downward forces as positive, plus 24 kilopounds is equal to 0. So V becomes minus 24 kilopounds. In this case, V is constant at section 2. Section 2 is between C and D. So V, our shear force, will be constant line between C and D. But it will be a linear curve between A and C, which will be minus 3x, which is a function of minus 3x. Okay, summation of moments is equal to 0. Let me consider counterclockwise moments equal to 0. Now remember that shear force is constant. So bending moment should be a linear function. Linear function of x. Okay. There is a moment M here. Shear force V does not produce any moment because it is acting at the same point where we are finding moment. Another force is 24 kilopound force. The same direction it is producing moment, 24 into x minus 4. It is the distance of x minus 4. So M will be 96 minus 24x. This is a linear function of x because shear force was constant. Similarly, if we section the beam at 3, we have this bending moment diagram. Shear force is downward, bending moment is counterclockwise. This 24 kilopound force is the same force. It is equivalent, a concentrated equivalent force to the distributed load. We have a 10 kilopounds downward force at point D and 20 kilopound feet moment here. Again, you can calculate it using summation of moments and summation of forces. So everything is in front of you. V and M between A and C, then V and M between C and D, then V and M between D and B. Now, V is a linear function of x or length between A to C, from A to C. So it is 0 to 8 feet. If it is linear, we can put 0 and 8 one by one in this expression. We will know the starting and end point, and we can draw a line between start and the end point. Similarly, in this expression, we can put values between 0 and 8, and we can find equation of moment. Between C and D, shear force is constant. We do not need to put any value here. Bending moment is linear, so we have to put values of x. From C to D, at C, x is equal to 8 feet, and at D, x is equal to, you can see here, from left end to C, it is 8 feet, and up to D, it is 11 feet. This is 11 feet from left end to D. So between 8 and 11. Similarly, from D to B, D is 11 feet and B is total length. So total length is 8 plus 3 plus 2 plus 3, 16. Between 11 and 16 feet. Okay, we will put values in these functions. Just below the free body diagram of the beam, at point A, x is equal to 0. We will draw shear force below the beam free body diagram. At point A, x is equal to 0, and at point C, x is equal to 8. The expression for this section, expression of shear force for this section was minus 3x. Shear force was equal to minus 3x. So if we put x equal to 0, it will be 0 at point A. If we put x equal to 8 feet at point C, so it becomes minus 24 kilopounds. Here is minus 24. This is a linear function, so we'll draw it with a straight line. Again, between B and C, between C and D, shear force is constant minus 24. It was already minus 24 in the previous section, and from C to D it is again minus 24, so it is constant. So shear force is minus 24 both at C and D. In the next section, from D to B, shear force is minus 34. So here is D and here is D. D is common between section CD and section DB. When we are drawing diagram of section CD, shear force was minus 24 kilopounds. And now when we are drawing between D and B, shear force is minus 34 at point D. So there are two values of shear force at point D, one in the previous section and one in the new section. So both are at the same point. We will draw a vertical line here. And then from D to B, it is constant, minus 34. It is constant. Remember that the shear force is equal to the concentrated forces at the ends. Here we have no concentrated force at point A, so shear force is 0. Here we have 34 kilopounds concentrated force at point B, at end B, so it is 34 here. The sign may vary, but the numerical value will be same. Okay, so if you are drawing shear force diagram, and you are starting from one end to the other end, and you are starting, you know the value of shear force. It is 0, and it should be 0 because in the free body diagram there is no concentrated force at the starting point. At the end, when you reach at the end and your value of shear force is same as the value of concentrated force at point B, so it means you have drawn the diagram correctly. Okay, if we move forward, we have bending moment expressions. Between A and B, bending moment was minus 1.5 x square. So if we put x equal to 0 here, bending moment will be 0. If we put x equal to 8 feet for point C, so put x equal to 8, m becomes minus 96 kilopound feet. So now we have to draw these 2 points, connect these 2 points. It is a parabolic curve because the equation is parabolic or quadratic. Now it can be drawn as a clockwise curve between A and C or a counterclockwise curve between A and C. Both can be quadratic. One method is to put the value of any point between starting and ending point, put a value of any x, for example x equal to 4, this, and if you see the value is above, here you can draw it clockwise. If it comes below the starting point, if it comes below this line, so you can draw it like here. Another method is, it is very easier one, if you remember this convention. Look at the shear force diagram. If the slope of the shear force diagram between 2 points is decreasing, the bending moment curve will be a clockwise curve. If the slope of a shear force diagram between 2 points is increasing, the bending moment curve between the same 2 points will be counterclockwise. So now we can see between A and C, the shear force curve has a decreasing slope. This slope is negative, decreasing. So the bending moment curve between these 2 points is clockwise. Similarly, if the shear force curve was a quadratic one, we have to see the, in this case it is linear, but for example if it is quadratic in some case, then we will see the slope of the load curve, and this convention is opposite. If the slope of the load curve is decreasing, the shear force diagram will be counterclockwise, and if the slope of the load curve is increasing, the shear force diagram will be clockwise. So here shear force diagram is decreasing, the slope of the shear force diagram is decreasing, it is a linear curve. So bending moment is a quadratic one, and due to the decrease in slope of shear force diagram, the bending moment curve here will be clockwise. Okay. Between point C and D, this is A, C, D and B. Between C and D, we have a function of bending moment equal to 96 minus 24x. Now put x equal to 8 feet for point C and x equal to 11 feet for point D in this expression. For 8 feet, you will get the same value, minus 96 kilopounds feet. For 11 feet, you will get minus 168 kilopounds feet. It will be a straight line, not a curve, because it is a linear expression. Again, the shear force is constant between C and D, so bending moment will be linear. Okay. Now, between D and E, D and B, between point D and B, the expression of bending moment function is 226 minus 34x. 226 minus 34x. Now put x equal to 11 feet for point D and x equal to 16 feet for point B. When we put x equal to 11 in this expression, we will get moment equal to 148 kilopounds. Now you can see at point D, there are two values of moment. In section CD, in this expression, if we put x equal to 11, we are getting moment at point D equal to minus 168 kilopound feet. For section DB, if we put x equal to 11 for point D, we will get value minus 148 kilopound feet, this one. So at the same point, we have two values, so we will draw a vertical line here. And then for point B, if we put x equal to 16 in this expression, we will get minus 314 kilopound feet. Again, between D and B, this expression is linear. Also, the shear force was constant between D and B, so the moment curve will be linear. Okay. So the first part of the problem was to draw shear force and bending moment diagrams, and you remember that there is no moment at point A of this free body diagram. So it is 0 in the bending moment diagram. There was a 318 kilopound feet moment at point B. So it is 318 kilopound feet at point B in the bending moment diagram. This is a verification. Okay. The first part has been solved. We were asked to find shear force, to draw shear force and bending moment diagrams. In the second part, we were asked to find normal stress just to the left and right of the point D. So here is bending moment diagram of bending moment diagram, and to the left and right, this is left side of the point D and this is right side of the point D. So section CD is on the left and section DB is on the right. On the left, we have different value of bending moment, and on the right, for point D, we have two values. On the right, we have a different value of bending moment. So left and right, immediate left and immediate right of point D has different bending moment values. So this one, minus 168 kilopound feet. We just need numerical value. The negative sign is not important for us. Minus 168 kilopound feet. Or 168 kilopound feet. 168 kilopounds means 1000 pounds, and feet, 1 feet is equal to 12 inches. So it becomes 2016 into 10 power 3, or 2016 kilopound inch. Kilopounds is 10 power 3. S can be taken from the appendix, from appendix C for a W10 112 rolled steel shape. S is equal to 126 inch about x-axis. Let us take this value from the book, W10 into 112. Here's the book, W10 into appendix C, W10 into 116. W10 into 116. Here it is. W10 into W10 into 112, I think. W10 into 112. Here is W10 into 112. Remember that the beam, the cross section, the I shape has, it is drawn along two axes, horizontal axis and vertical axis. If it is not given to us that along which axis the beam is lying, so we will suppose it in this orientation where x is the horizontal axis and the beam will bend about the horizontal axis, x-axis. So we will find shear modulus, section modulus about x-axis. If it is given in this orientation, then we will find it around y-axis. Okay, then this is our horizontal axis y. But if it is not given, just like in this problem, it is not given, so the natural orientation is this one. So we will find section modulus Sx. So Sx for W10 into 112 beam is 126 cubic inch. Here is the unit, 126 cubic inch. It is 126 cubic inch. We have taken it directly from the table. So by putting the values in this expression, we can find maximum stress just to the left of the point D. Similarly, on the right of point D, it is 148 kilopound feet. So 148 into 12 into 1000, 148 into 12 into 1000, so it becomes 148 into 10 power 3 pound inches, or 148, sorry, it is not 140, 148 into 12 into 1000 becomes 1776 pound inches. So it is 1776 kilo pound inches, or 10 power 3 pound inches, divided by same section modulus. Geometry is same either at the left or right of the beam of the point D. Cross section will be same, so maximum stress is 14.1 ksi. It was asked in the statement of the problem to find normal stress just to the left and to the right of the point D. The next topic is relations among load, shear and bending moment. Previously we have calculated, we have drawn shear force and bending moment diagrams by sectioning the beam. Now we will derive some relationships between load and shear force, so that we can find expression for shear force from the load, and then a relationship between bending moment and shear force. So in this topic we will discuss those relationships. Here is a beam given under random distributed load W. If we consider a section of the beam C dash, I want to cut this beam, section this beam at C and at C dash. This length is very small one, delta x, and delta x is a negligibly small number, small length, so that we may consider this load as a rectangular load, like this one. I will consider this as a rectangular load because delta x is a very small number, small length. So we will draw a free body diagram here. On the left side at section C, there will be an upward shear force and a clockwise moment. Similarly, on the right side there is a downward shear force V plus delta V and a counterclockwise moment M plus delta M. If we consider it as a rectangular load, because the thickness is very small, so variation is also very small, variation in the load, distributed load. So we are considering it as a rectangular distribution, uniform distribution. If we replace this uniform distribution with a concentrated load, it will be load into length delta x, so it becomes W delta x, the concentrated load, and it acts at the centroid of the rectangle, which is half of delta x. Now I want to draw a relationship between load and shear force. I will apply equations of equilibrium on this free body diagram. For relationship between load and shear force, I will consider summation of forces in y direction is equal to 0. So there are three different vertical forces. Force V, if I consider vertical upward forces as positive, V is upward, minus V plus delta V, it is downward, and minus W delta X, it is also concentrated load, downward concentrated load. Okay, some terms will get cancelled out. V and minus V will cancel out, so it becomes delta V is equal to minus W delta X, or delta V by delta X is equal to minus W. If I take, since delta X is a very small number, so I want to take limit on both sides. Limit delta X tends to 0, delta V by delta X is equal to limit of the right side. So it becomes dV by dx. On the other side it is minus W. Or we can further rewrite it as integral R. We can write it as dV is equal to minus W dx. If this is a relationship between load and shear force, derivative of shear force with respect to x or length is equal to minus distributed load. If we want to find shear force between any 2 points, for example between point C and D, if we know one of them at either shear force at C or D, we can find the other one. How we can do it? We have to integrate this expression. It will be Vd minus Vc, shear force at point D minus shear force at point C is equal to integral of W dx from xc to xd. Location at C and location at D. This is the relationship between shear force and distributed load. Similarly, we can derive a relationship between bending moment and shear force. How can we do it? By taking summation of moments at C dash equal to 0. Here is C dash. There are different moments here. First one is, if I take counterclockwise moments as positive, the first one is m plus delta m. Then this clockwise moment m. Then there is one moment due to this force V. V is also clockwise, V into its distance from C dash, it is delta x. This force V plus delta V does not produce any moment at the point C dash because it acts at the same point. Then this this concentrated force W delta x is producing a counterclockwise moment around C dash. Okay, now if we simplify it, m and minus m will cancel out. We have delta m is equal to V delta x minus 1 over 2 W delta x square. Now if we divide both sides by delta x, this will become delta m by delta x is equal to V minus 1 over 2 W delta x. If I take limits on both sides, where delta x tends to 0, here it will become differential of m moment with respect to x. Here the second term involves delta x, and since delta x is a very small number, due to limit it becomes 0, so here will be V only. This is a relationship between bending moment and shear force. Or if we want to integrate it, it will be bending moment between any 2 points C and D will be integral of shear force from location of C to location of point D. We may use these two expression of the relationship between shear force and load, and the relationship between bending moment and shear force, to find shear force and bending moment if load is given to us. If load is given, we can find shear force from this expression, and then from the same shear force we can find bending moment using these two expressions. Here's a sample problem 5.3 on the same topic. Draw the shear and bending moment diagrams for the beam and loading shown. Okay, before this I want to explain one more fact. Integral of load, this expression means either if we have the expression, if we have load as a function of x, so we can integrate it, or if we find area under the load curve. Integral is actually area under the curve. So area under the load curve between point C and point D means integral of W with respect to X between point C and D. Similarly, in this expression, if we know expression of shear force V with respect to, in terms of X, we can integrate it. Otherwise, area under the shear force curve between point C and point D will be equal to the right hand side of this expression. And remember that this expression is between a relationship between shear force and distributed load. W is distributed load. It is not for concentrated loads. Remember that whenever there is a concentrated force, shear force will be equal to the concentrated force, and it will remain constant between a concentrated force and a distributed force, or between two concentrated forces. So we will move towards our sample problem. Draw the shear and bending moment diagrams for the beam and loading shown. In this beam, we have two concentrated forces at point B and C, each 12 kilopounds. Then a distributed force between D and E, which is 1.5 kilopounds per feet. And there are two reaction forces, one at point A and the other at point D. First, we will find reaction forces at A and D using equations of equilibrium. Here are them. By taking summation of moments at point A equal to 0 and summation of forces equal to 0, we can find reaction at A and D. You can do it by yourself. This is part of your engineering statics knowledge. Once we have reactions at A and D, this reaction will be 0. X will be 0 because there is no other force in X direction. So summation of forces is equal to X in X direction is equal to 0. So AX will be 0. And we do not need longitudinal forces in beams. We only need transverse forces for these calculations, shear force and bending moments. Okay, here is the free body diagram. This one. At point A, we have a concentrated force. Again, at point B, there is another concentrated force. At point C, there is a third one. At point D, there is another upward concentrated force. And from D to E, we have distributed loads. So remember that between each two concentrated forces, the shear force will remain constant. We do not need to apply any relationship between concentrated force and shear force. Shear force is directly equal to concentrated force at a point. It is a difference between actually. Shear force is difference between concentrated forces between two consecutive points. For example, at point A, there is a 18 kilopounds upward force. The shear force will be equal to 18 kilopounds, positive 18 kilopounds at point A. It will remain constant till point B. And then at point B, we have another concentrated force, 20 kilonewton. 20 kilopounds. So it is downward, so it is minus 20 actually. We will add the previous 18 with minus 20. 18 minus 20, it becomes minus 2. I will move forward to show it to you. Apply the relationship between shear and load to develop the shear force and shear force diagram. This relationship is for distributed loads only. W is distributed load. Zero slope between concentrated loads. Between two concentrated loads, slope will be 0. And linear variation over uniform load segments. Uniform load segment is simply a horizontal line. It is uniform, so the shear force will be 1 degree higher. It will be linear. So let us start here. At point A, there is positive 18 kilopounds shear force. At the starting point, shear force will be equal to the concentrated load at that point. If it is upward, it will be positive. If it is downward, it will be negative. If there is no concentrated force at the starting point, there will be 0 shear force. So at point A, we have positive 18 kilopounds shear force. Then there is no distributed load between A and B. So shear force will remain constant. This horizontal line is constant shear force. At point B, there is downward 20 kilopounds force. So previously we have 18 kilopounds, minus 20 becomes minus 2. Now from B to C, there is no other distributed load. So shear force will remain constant again. So it will remain constant at minus 2. Remember that we have two values of shear forces at point B. One is 18 and the other is minus 2. The 18 kilopounds came from section AB and the minus 2 kilopound is between section B and C. Then at C, again we have a downward force of 12 kilopounds. Previously we have minus 2 and downward 12 is minus 12. Minus 2 minus 12 becomes minus 14. So at point C, we have two values of shear forces. Between section BC it is minus 2, between section CD it is minus 14. From C to D, again there is no distributed force, so the shear force will remain constant. There is zero slope, it is constant. At point D, we have an upward force of 26 kilopounds. Previously we have minus 14 and upward 26 is positive 26. So minus 14 plus 26 becomes plus 12. Again at point D, we have two values of shear forces. One between section CD, it is minus 14, and the other at the right side of D is plus 12. Between D and E, we have a distributed load. So we have to integrate it between D and E. Or we can simply find area under this curve. If we find area under the curve, 1.5 multiplied by 8. This is simple rectangular distribution. So 1.5 multiplied by 8 becomes 12. And since it is downward, so we will call it minus 12. Plus 12, previously we have plus 12, the new value is minus 12. Plus 12 minus 12 becomes 0. And we have to join it with a linear line because load is constant. If load is constant, shear force will be 1 degree higher. It will be linear. Alternatively, here, previously we know the value of shear force at point D. It is plus 12 VD minus VE. Sorry, I will write it as VE minus VD is equal to minus integral of W dx from xt to xe. Okay, VD is known to us. It is 12 minus 1.5 x xd and xe. xd is distance of point D from point A from the left end. It is 6 plus 8 plus 10. It becomes 24. 24. And xe is distance of point E from point A from the left end. It is 6 plus 8 plus 10 plus 8. So it becomes 32. So VE minus 12 becomes, sorry, this is 1.5 dx. It becomes 1.5x from 24 to 32. It will become minus 12. So VE xe minus 12 is equal to minus 12 VE. This is VE. VE becomes 0. This is how you do it mathematically. Previously, I have told you that simply you can find area under this rectangle, which is 1.5 into 8 becomes 12. It is downward, so we will consider it minus 12. Adding minus 12 with the previous value, which was plus 12, it becomes 0. So this is how we draw shear force diagram. Now we have to find area under the shear force diagram to draw a bending moment diagram. Okay, this area is simply 18 multiplied by its length. Length is 6. 18 into 6 becomes 108. This will. Area under the next rectangle, this one, minus 2 into 8. Minus 2 into 8 is minus 16. The next one is minus 14 into the length, it is 10. Minus 14 into 10 is minus 140. And this is a triangle. Area of triangle can be found by using 1 over 2 into base into height. Base is 8 and height is 12. So it becomes plus 48. Now we know area under the shear force diagram. So we can find bending moment diagram here. The bending moment is simply integral of shear force md minus mc between 2 points C and D. It is integral of shear force between points C and D, or area under the shear force diagram. Okay, at starting point A, at the left end, there is no bending moment applied. If there is no bending moment applied in the free body diagram, there will be zero moment at the specific end. So at end A, there is no bending moment, so it is 0 here. At this point A, then between point A and B, we have 108 kilopounds feet area under the curve. So 0 plus 108 becomes 108. And since we have a point here, since shear force curve is constant, so moment will be 1 degree higher, it will be linear. Then the next is the next area between point C and D, A, B, C, D. Next area between B and C is minus 16. So we will add minus 16 with the previous value 108. So 108 minus 16 becomes plus 92. Here again shear force is constant, so bending moment will be linear. The next area under the shear force curve between C and D is minus 140. So adding minus 140 to the previous value plus 92, plus 92 minus 140 becomes minus 48. Again, shear force was constant, so bending moment will be linear. Okay, the next area under the shear force diagram between D and E is plus 48. We will add it to the previous value, which was minus 48. So plus 48 and minus 48 becomes 0. Shear force is linear, so bending moment will be quadratic. Now it can be clockwise quadratic or counterclockwise quadratic. It can be like this, or it can be like this. Which one to follow? So we will see. This is a convention. If the slope of shear force curve between 2 points is decreasing, the bending moment curve will be counterclockwise. And if it is increasing slope, the shear force curve slope is increasing, then the bending moment curve will be if the shear slope curve is decreasing, if the shear force curve between 2 points is decreasing, the bending moment curve will be clockwise. If the shear force curve between 2 points is increasing, the bending moment curve will be counterclockwise. So here it is decreasing slope between D and E. So we have a clockwise bending moment curve. If the slope between D and E was increasing, then this curve must would have counterclockwise. Okay. So this is how to draw shear force and bending moment diagram using relationship between using relationship between load, shear force, and bending moment. We simply need to know the area under the shear force curve and the bending and the load curve. Okay, here also we can do it like between mathematically we can do it mb minus ma integral of v dx between xa and xb. Now ma is known to us, it is 0. mb minus 0, area under the shear force curve integral, or you can say shear force between A and B was 18. XA is 0 and XB is distance of point B from point A, it is 8. MB becomes 18x from 0 to 8. You can simply multiply 18 with the number 8 and you can find it as, sorry, this is maybe distance between A and B is 6 feet, not 8 feet. Here it will be 6. So 18 multiplied by 6 becomes 108. MB becomes 108 like this one. Similarly, if you want to find MC, it will be MC minus MB is equal to integral of V between point B and point C. So MC is unknown to us, MB is 108. V between C and D is minus 2. This one. XB is 6 and XC was 14. It is between distance from A to C. Distance from A to C is 6 plus 8. It is 14. So if you simplify this one, it must come out as 92. Similarly, you can do it between C and D and D and E. So this was required from us to draw shear force and bending moment diagrams for the beam and loading shown. Okay, our next problem is sample problem 5.5. The statement is, draw the shear force and bending moment diagrams for the beam and loading shown. Here, the cantilever beam is given. A distributed load, linear distribution between A and B is given. The length of the load is small a and the maximum load is minus u naught. Now we have to draw, we have to find relationship between shear force and bending moment using the standard integral method. In a relationship between shear force and bending moment is like this. Okay. For this, first we need to know the reactions at point C. This is a cantilever beam, so we must have 3 unknowns: one vertical force, horizontal reaction force, and a moment. Horizontal reaction force is equal to 0 because there is no other horizontal force. summation of forces in y direction is equal to 0. First, we have to actually convert this distributed load into concentrated load. It will be 1 over 2 W naught A. And the distance from here is, it is A by 3. Okay. So RC, here is RC. RC minus 1 over 2 W naught A is equal to 0. So RC becomes 1 over 2 W naught A. Similarly, summation of moments at point C is equal to 0. So we have MC and a moment due to this load. This distance is 2A by 3. Okay, you can do the calculus part, the statics part by yourself. We have found reaction force and reaction moment at point C. Now, first we have to use the integral relationship between shear force and the load. For that, we need to know the equation of this load line. For line, we have an expression of y is equal to mx plus c. M is slope and c is the vertical intercept. Here, W is the load. It is equal to M. M is slope. Slope is W naught over A. But since it is decreasing, so it will be minus W naught over A into X plus C. What is Y intercept? This is Y intercept, vertical intercept. It is W naught. So this expression becomes W naught 1 minus X over A. This is expression of this line. Now we will use the expression VB minus VA is equal to integral of minus W dx XA to XB. The expression of W is given to us, not given, we have already found it out. So we will use this expression of W in the integral, W naught into 1 minus X by A, W naught into 1 minus X by A, this one. Okay, VA, what is VA? VA, simply point A is the end point. So we will see if there is any concentrated force at the end point. If there is any concentrated force at the end point, VA will be equal to that force. If there is no concentrated force at the end point, VA will be 0. So we can see here there is no concentrated force at point A, so VA is 0. We can integrate this expression W naught into 1 minus X by A. W naught is constant. Integral of 1 becomes X, and X integral of X becomes X square by 2. Okay, from 0 to A. Now if we put 1 by 1, if we put A into this expression and then 0 into this expression and simplify it, so VB becomes 1 minus 1 over 2 W naught A. This is simply area under the distributed load. We can also find it here using the area under the rectangle expression, which is 1 over 2 W naught A, and since it is downward, so it becomes negative. Anyways, VB has been found. VA was 0. There is no concentrated force at end point. VB is minus 1 over 2 W naught A. They need to be connected using a quadratic line because load is linear, so shear force must be quadratic. It should be 1 degree higher, or otherwise we can see it here. The expression is a quadratic expression. Now there is another convention. Previously we explained relationship between bending moment and shear force. If the shear force diagram between 2 points has a decreasing slope, so bending moment curve will be clockwise. Here it is opposite. If the load curve If the slope of the load curve between 2 points is decreasing, just like between point A and B, it is decreasing. So the shear force curve will be counterclockwise. So here it is, counterclockwise. Then from B to C, there is no distributed force between B and C. So the shear force will remain constant. It is constant. You can see that at the end point at C, the shear force is minus 1 over 2 W naught A. It is similar as the concentrated force at point C. So this means our calculations are correct. The concentrated force at the end point is equal to the shear force. So here the sign may vary. Here our shear force is same as the concentrated force. Okay. Now to draw the bending moment diagram, we either need to know the area under the shear force curve or we have to integrate it. So area under the shear force curve can be found here. This is a parabolic curve. Area under this curve will be 2 by 3 into base into height. Base is A and height is minus 1 over 2 W naught A. So it becomes minus 1 over 3 W naught A square. Similarly, this is a rectangle. So area of rectangle is easy to find. Height is given to us minus 1 over 2 W naught A and length is L minus A. So height into length becomes minus 1 over 2 W naught A into L minus A. Or if we want to use integral method or integration, we have to use this expression of shear force. This is shear force between point A and point B. So moment between B and A, MB minus MA is equal to integral of shear force between B and A. This was expression between B and A, expression of shear force. If we integrate it, it becomes minus W x square by 2 minus x cube by 6A between 0 and A. MA is 0 because there is no concentrated moment at point A. So MB can be calculated, which is minus 1 over 3 W naught A square. We found the same value here by finding area under the curve, minus 1 over 3 W naught A. Again, between C and B, MC minus MB is equal to integral of shear force between B and C. So shear force between B and C is constant minus 1 over 2 W naught A into dx. Location at point C is distance from location at point B is equal to distance from A to B, which is A, and location of point C is distance between A and C, which is L. So by integrating it and simplifying, we can find MC is equal to minus 1 over 6 W naught A into 3L by minus A, or A W naught over 2 into L minus A by 3. This value after simplification, or this one, here it is, this one, this value and this are same. Okay. Results at C are compatible with the free body diagram analysis. How they are compatible with the free body diagram analysis? This value of moment is same as the moment found at C using equations of equilibrium. So they are compatible. One more thing, the shear force diagram between between A and B has a decreasing slope. The slope is decreasing. So bending moment diagram is clockwise. And then shear force is constant between between B and C. So it is linear here. The bending moment diagram is linear. We will move forward. The next topic is design of prismatic beams for bending. Previously, we know that from chapter number 4 that the maximum normal stress is equal to mc over I or m over s. This expression. Here, if the moment is maximum, previously we didn't discuss about maximum moment. We were only discussing about the cross section of the beam. The moment does not depend upon the cross section. Now we have drawn the bending moment diagrams. So wherever the moment is maximum, for example, in the previous topic, moment is maximum here, so stress will be maximum at this point. In the previous problem, moment was maximum here at 108 at point B, so stress will be maximum here. So from the bending moment diagram, we can find maximum moment. The maximum stress is usually equal to the allowable normal stress, and it is given for different materials if we know the factor of safety of for the application and the yield strength of the material. Now, using the maximum value of maximum stress and maximum moment, we can find the minimum section modulus of the beam. This is the minimum safe section modulus. The section modulus can be more than this but cannot be less than this value, the design value. Section modulus is a geometric property of the material. For rectangular beam, section modulus is equal to 1 over 6 bh square. Section modulus is simply moment of inertia divided by c. What is c? C is distance from the neutral axis to the outer surface of the beam. Okay, so we can design a beam, we can find its geometry, its section modulus using this expression, maximum moment divided by allowable bending stress or allowable normal stress. We will move towards the, okay, before that, among beam section choices which have an acceptable section modulus, the one with the smallest weight per unit length or the cross-sectional area will be the least expensive and the best choice. Once we find the minimum section modulus value, then we will go to the table of different beams, properties of the beam, or we go to market and we find either we have a beam with section modulus more than this defined value, this minimum value. Among those beams, if there are multiple beams, we have to choose the beam with smallest weight per unit length or smallest weight per unit cross-sectional area, because those beams will be least expensive among all. Okay, we will do this in our problem, and the sample problem 5.8. A simply supported steel beam is to carry the distributed and concentrated loads shown in the diagram. Knowing that the allowable normal stress for the grade of steel to be used is 160 megapascal, select the wide flange shape that should be used. Beam has been given, loading is given. It is made of steel and it has allowable normal stress, sigma allowable, which is equal to sigma maximum. It is 160 megapascal. We have to choose the wide flange shape beam. Wide flange means W beam. At the end of the book, there is a appendix C where we have data regarding wide flange beams and short flange beams, W beams and S beams. So from this, in this problem, we will find S minimum using the expression maximum moment over sigma allowable or sigma maximum. Sigma maximum is given to us. Maximum moment can be found using bending moment diagram. Then we can find S minimum. Once we find S minimum, we will go to the textbook, and appendix C, we have properties of rolled steel shapes, W shape beams. Similarly, we also have S shape beams on the subsequent pages. Here are W, these are Ws. Here are S shape beams, S-shaped beams, S-shaped beams. Okay, so we have to find numerical value of S minimum. For that, first we have to draw maximum bending moment diagram. Before that, find unknown reaction forces at point A and point D using equations of equilibrium. You can do it by yourself. Here are summation of moments and summation of forces is equal to 0. Two expressions. We can find reaction at point D and reaction at point A. You can do it by yourself. Okay, at point A, we have 52 kilonewton force. So upward 52 means positive 52 kilonewton shear force. Then we have a distributed load. This distributed load is equal to 20 kilonewton per meter. This is per meter. 20 kilonewton per meter. This is concentrated load, equivalent to this distributed load. Okay, 20 kilonewton multiplied by its length. So 20 multiplied by length is 1.5 plus 1.53. 20 multiplied by 3 becomes 60. So area under the distributed load between point A and B is 60 kilonewton meter. So plus 52 minus 60, because it is downward, plus 62 minus 60 becomes minus 8. At point B it is minus 8 kilonewton. So we have to draw a line between point A and point B. Since the load is uniformly distributed, the shear force will be linear. So here is a line, straight line. Then there is no force between B and C, so it will remain constant, minus 8 kilonewton. At point C, there is a downward force of 50 kilonewton, so minus 8 is already there. Then downward 50 kilonewton means minus 50 kilonewton. So minus 8 minus 50 becomes minus 58. Between C and D again there is no force, so it will remain constant up till point D, minus 58. And you can see at point D we have 58 kilonewton force. So our answers or our diagram is correct. Okay. We have drawn a shear force diagram, but actually we need a maximum bending moment. Either we have to draw a bending moment diagram, or we can find maximum bending moment from here as well, from the shear force diagram as well. Before that, I will draw a bending moment diagram, and then we can also find another method, discuss another method how to find maximum moment from the above diagram. Bending moment in kilonewton meters. At point A, there is no bending moment in the diagram, so I will write it here as 0. At point B, first we have to find area under the curve between each 2 points. Between point A and E is a triangle. This becomes, the area will be 1 over 2 into base into height. Base is 2.6 and height is 52. So how we have found this 2.6, I will discuss it later. So it becomes 67.6. Okay, this distance is 0.4 meters and the height is 8. So we can also find this area. This will be 1 over 2 into 4 into 0.4 into 8. It becomes 1.6. Okay, this rectangle has a length of 1 meter and height of minus 8. This is also minus 1.6. This is minus 8. And this rectangle has a length of 1 meter and a height of 58, so it becomes minus 58. Okay, we will draw bending moment diagram. At point A in the diagram, free body diagram, there is no bending moment. So at point A, it is 0. At point E, we will add area under the curve, which is 67.6. 67.6 with the previous value 0 becomes 67.6. From B to E to B, it is minus 1.6. So 67.6 minus 1.6 becomes 66. Point B, it is 66. Between B and C, area under the shear force diagram is minus 8. So 66 minus 8 becomes 58. And from 58, from point C to D, again we have area under curve equal to minus 58. So plus 58 minus 58 becomes 0. Now, from A to E, we have a decreasing slope of shear force. So here will be a clockwise bending moment diagram. From E to B, again we have a decreasing slope. Again, it will be a it will be a clockwise bending moment diagram. Quadratic. Both of these curves are quadratic because the shear force is linear. Between C and B and C, the shear force is constant, so bending moment will be linear line. And again, between C and D, the shear force is constant, so it will be linear. So maximum bending moment is 67.6. We have to take the value only, not the sign. Even if it was negative, the magnitude is important for us. The maximum bending moment is 66.7. Alternatively, if we do not want to draw this diagram, we can find it again. The bending moment, we can still find it. Bending moment is maximum where shear force is 0, because derivative of bending moment is equal to shear force. So a function is maximum where its first derivative is equal to 0. We have studied it in mathematics regarding maxima and minima. So bending moment will be maximum where its first derivative is equal to 0. So we will see where shear force is 0. Shear force is 0 at point E. So bending moment will be maximum till point E, which is then we have to find this distance between A and B. How we have found this distance between point A and point E? We know that bending moment will be maximum at point E. Okay. We have to find this distance between A and E. If we call it X, this distance will be 3 minus X. Since these two triangles A dash, E and B dash, E are similar triangles, this ratio of their corresponding sides will be equal. So if I take ratio of their corresponding sides, it will be 52 by 8 is equal to X divided by 3 minus X. So we can find X from this expression. This 52 divided by 8, this height is 8, X divided by 3 minus X. So X becomes 2.6 meters from here. We know X, which is 2.6, so we can find area under this curve, this triangle, this 67.6, and it is maximum. So either use this method, or if you want to draw bending moment diagram, from both the methods you can find maximum moment, which is 67.6 kilonewton meters. Maximum moment has been calculated, 67.6 kilonewton meter. Kilonewton means 10 power 3 newtons, and here sigma allowable was already given. It is 160 megapascal, so megapascal means 10 power 6 Pascal. So we can find S minimum, which becomes 422.5 into 10 power minus 6 meter cube. We want to convert it into millimeter cubes. 1 meter is equal to 10 power minus 3 meters. 1 meter is equal to 10 power 3 millimeters. So 10 power 3 into power 3 becomes 10 power 9 and into 10 power 9 and 10 power minus 6 becomes 10 power plus 3. So it becomes 422.5 into 10 power plus 3 millimeter cube. Now we will go to, I have converted it into millimeters because the values in the appendix C, values of section modulus in the appendix C are given in millimeter cube. I will go to appendix C and find which beams. Okay, here are two axes given, x-axis and y-axis. If we see at the diagram, this is our horizontal axis, x-axis. Usually the W beams or the I beams are kept in the given orientation. In the problem, it is not given, the orientation of the beam is not given. Otherwise, if it is in this orientation, we will find I around this axis, which is Y in this case. But naturally they are in this orientation, given orientation. So we will find SX. Sorry, this is an inch cube, and our problem is in meters. So we will see the one given in SI units. This one. This is in millimeters. So we will see 422 into 10 power 3 is already given here. So for any value more than 422, this one is more than 422, this is more than 422, this value, all those values which are more than 422, because S minimum is 422, so we have to find value more than S minimum. These beams, W360 into 32.9, 39, 44, 57.8, all these beams have S value, section modulus around x-axis more than the calculated S minimum. Which one to choose? All these values are more than S minimum. Now we have to find which beam has lesser weight. So how can we find weight of the beam? Here it is given. A wide flange shape is designed by the letter W, followed by the nominal depth in millimeters and mass in kilograms per meter. So after W, the first value is depth of the beam and the second value is mass per meter. So we will find which value has, which beam has lesser mass or lesser weight. So I will list out all those beams, all those values more than 422. Here are the values more than 422. W410 into 338.8 has S value 637. Similarly, 477, 474, 549, 535, 448. Among all of them, the beam with minimum mass is the minimum second number. Among them, this one has minimum second number, 32.9. It has least mass per unit meter. So this beam is our chosen beam, is the design beam. 360 into 32.9. This was asked from us in the problem to select a wide flange shape. So we have selected this shape, W360 into 32.9. We will move further. Next topic is singularity functions used to determine shear and bending moment. This is a very important topic. Why it is important? Because before this topic, we have discussed two topics, either by sectioning the beam or drawing shear force and bending moment diagram by sectioning the beam, or using the relationship between load and shear force, similarly shear force and bending moment. In the previous methods, we were able to find shear force and bending moment between different sections, between two different points in different sections, but we couldn't write a single expression for shear force for the whole beam or a single expression of the bending moment for the whole beam. Now in the singularity method or the singularity functions, we will be able to write single expression of shear force for the whole beam. Similarly, a single expression of bending moment for the whole beam. On the slide, a beam has been given, beam AB, where there is a distributed load between point B and point C. Using the previous method, if we want to write shear force and bending moment expressions, first we have to section this beam between A and C, and then between B and C. Section 1 and 2. Before that, we will find unknown reaction forces. In this case, the unknown reaction force at A is 1 over 4 W naught A. If we section it at section 1, there is a downward force V1 and moment M1. Similarly, at section 2, there is a downward force V2 and moment M2. We can write between x between 0 and A expression for shear force and expression for bending moment. You can do it by yourself. Similarly, between A and 2A, we always count distance from the left end. So between A and 2A, we have V2 and M2. Now if we see what is the difference between V1 and V2, this second term. This is the difference between these two shear forces. Similarly, between M1 and M2, this second term is the difference. The first terms are same. Now if we write a single expression for shear force and bending moment using this expression of V2 and M2, but the second term has been written in terms of Macaulay brackets. These are Macaulay brackets. If the second term is 0, the expression of V is equal to V1. If the second term is not 0, the expression of V is equal to V2. Similarly, if the second term is 0, the expression of moment will be M1. If the second term is not 0, the expression of moment will be equal to M2. You can see it here. The difference is only the second term. If the second term is 0, it is M1. If the second term is not 0, it is M2. Similarly, in case of V, if the second term is 0, it is V1. If the second term is not 0, it is V2. So we have written a general expression where the second term has been written in special brackets, Macaulay brackets, and we call it singularity function. This function in the brackets x minus a is called singularity function. If the singularity function is 0, the second term will vanish out and expression of shear force and bending moment will become those of V1 and M1. And if the second term is not 0, those will be V2 and M2. The second term can only be 0 if x is equal to a. And also, if x is less than a, the x minus a will be less than 0. It will be negative, and we will again neglect the term. Remember that anything into the Macaulay bracket, if it is 0 or negative, we will neglect the whole bracket, whole term. Here we can see if x is between 0 and a, x is less than a. We are in the first section between a and c, and expressions for v1 and m1 will hold. If x is less than a, x minus a will be negative, it will be less than 0, and the bracket will vanish out and this term will be cancelled out. The second term in each function is included in the computation when x is greater than a or equal to a. When x is greater than a, x minus a will be a positive number. When x is equal to a, x minus a will be equal to 0 and the bracket will finish out. When x is less than a, x minus a will be negative, and again we will neglect the whole term. So if x is less than a, we will ignore the term. If x is equal to 0, a is equal to a, automatically anything in the bracket will be 0 and the term will be neglected. If x is greater than a, so it will be a positive number. Furthermore, using the same convention, the distributed load at any point of the beam can be expressed as distributed load at any point can be written as W naught into x minus a power 0. If anything inside this bracket is positive number power 0 will be equal to 1, so W will be equal to W naught. Okay. So anything inside the bracket, x minus a, power 0, power 1, power 2, or anything power n, they are called singularity functions. The singularity function x minus a power n will be equal to x minus a power n into a normal bracket, normal parenthesis, when x is greater than or equal to a. If anything inside this bracket, if x is less than a, anything inside this bracket will be neglected, will be equal to 0. Okay. So remember that once, whenever we solve, we use singularity functions method, we will see anything in the Macaulay brackets. If it is negative, we will neglect the whole term. If it is 0, already the term is neglected. If it is positive, we will consider the term itself. The Macaulay brackets will be replaced with regular parentheses. Okay. Whenever the quantity between the Macaulay brackets is positive or 0, the brackets should be replaced by the ordinary parentheses. Whenever the quantity is negative, the bracket itself is equal to 0. The three singularity functions corresponding to n is equal to 0, n is equal to 1, and n is equal to 2 have been plotted in the figure below. The horizontal axis is x-axis, the vertical axis is x minus a power 0. If x is less than a, x minus a will be negative, and we will neglect this whole term. It will be equal to 0. Between a and b, it is equal to 0. If x is equal to a, again, it will be 0. A minus a is 0. If x is greater than a, in this region, this is x is less than a region. If x is greater than a, so x minus a will be a positive number. Any positive number, power 0 is equal to 1. So this is constant. Okay. X minus a power 1 versus x. If x is less than a, so the term itself will be neglected. If x is greater than a, so it will be a positive number. But power 1, x power 1 means it is a linear expression, so it will increase with x linearly. Similarly, x minus a power 2. So between x and a, where x is between 0 and a, where x is less than a, this term is 0 because anything inside the bracket will be negative. For x greater than a, it is a positive number, but power 2 means a quadratic number, and it will be a quadratic curve. Okay. Here are some standard expressions for shear force, loading, shear force, and bending moment for different types of loads. The first column shows loading, the second shear force, and the third bending moment. If the load is a simple bending moment at distance a from the left end, so there is no expression for bending, for loading, no expression for shear force. It is only bending moment, and the bending moment will be equal to minus m into x minus a power 0. Remember that we have to use this table while solving numerical problems. If the given loading is a concentrated load, downward concentrated load P, at a distance A from the left end. There is no loading function. Singularity function for shear force will be minus P into x minus a power 0. The singularity function for bending moment will be minus P into x minus a power 1. Remember that bending moment function is always 1 degree higher than shear force. It is 1, shear force was 0. And the load function does not exist. For a distributed load, uniformly distributed load W naught at a distance A from the left end, it has a loading function W is equal to W naught into x minus a power 0. It has a loading function. Shear force is 1 degree higher and bending moment is again 1 degree higher than shear force. Remember that this distributed force has a distance A from left end and it is closed at right end. It has reached at the right end. So if a given load is not closed at the right end, we have to close it by ourselves. How we will do it, I will explain it later. Okay, if the given loading is linear distribution with the slope k, slope is simply height divided by base. Okay, so it has a distance a from the left end. It is closed at the right end again. Remember that it is closed at the right end. It has a load function of W is equal to K into x minus a power 1, where K is the slope. Here V is equal to shear force function and M is the singularity function for moment. If the load is a higher degree curve, it can be quadratic, cubic, or any higher degree n. So W is equal to K into x minus a power n. V will be minus K over n plus 1 into x minus a power n plus 1. And M will be minus K over n plus 1 into n plus 2 multiplied by x minus a power n plus 2. Use of open-ended loadings to create a closed-ended loading. For example, a load is given like this. A distributed load is given, W naught. It has a distance A from the left end, but it is not closed at the right end. So we will add some load here. Whatever load we have added, downward we will add similar load upward as well. If it is W naught, this will be W naught. So we will make it here like this. Now we have two distributed loads, one downward and the other upward. Both have distances from the left end, A and B, and both are closed at the right end. We can apply singularity functions on these two loads. We can only apply singularity functions on the given conditions given in this table, like these two, case D, case E, C, B and A. Here the white background means there is no function for these conditions. The dark background means this is the first function of the same of this specific case. For this case, the first function is moment function. There is the shear and loading functions do not exist. Here, the first function is of that of shear force. Loading function does not exist. For case C, the first function is that of load function. Okay, we will move. There is a sample problem 5.9. For the beam and loading shown, determine the equations in part A. Determine the equations of equations defining the shear force and bending moment at any point. At any point means here equations defining shear force and bending moment at any point. At any point means we need to have a single expression for the beam where we can find any value of x and we can find the shear force and bending moment. So it is not written here to use singularity functions. but to define an equation which can give us shear force and bending moment at any point means we have to write a singularity function equation. In part B, the shear force and bending moment at points C, D and E. Once we have general expressions from part A, general expressions of shear force and bending moment, we can put the values of x for point C, D and E to find shear forces and bending moment at C, D and E. Okay, before anything, we have to draw a free body diagram and find reaction forces at point A and B. You can do it by yourself. Simply convert the two triangles into concentrated forces to find their to apply the equations of equilibrium and find the reaction forces at A and B. Here it will be a concentrated force 1 over 2. The base is L over 2 and height is W naught. L over 2 into W naught. Similarly, this one is 1 over 2 L over 2 W naught. So because 1 over 4 L W naught. So each concentrated force is 1 over 4 W naught L. 1 over 4 W naught. You can do it by yourself. Now this distributed load is not of the same form which is given in the standard table. In the standard table, we have linear distributions having a distance A from the left end and they are closed at the right end. So here, this triangle has 0 distance at the left end. A is equal to 0 here, but it is not closed at the right end. How we can close it at the right end? We can extend this triangle here with the same slope. So at L by 2, if it is W naught, so at full L with the same slope, it will be 2 W naught. We have added W naught at this end and 0 at point C, 2 W naught at end B and 0 at point C. We will add upward load here. Now we have two triangles. One triangle with downward load at a distance A equal to 0 from the left end, and the other triangle at a distance A equal to L by 2 from the left end. Here like this, we have extended the load up to 2 W naught, and then upward load of 2 W naught at point B and 0 at point C. We have two triangles. The upper triangle has a slope equal to 2 W naught divided by entire length, so 2 W naught divided by L. This is positive slope. And the bottom triangle, which is upward load, has a slope equal to 2 W naught divided by L by 2, half length, so it becomes minus 4 W naught over L. It is negative slope. Here are the two triangles. First, we will write load function for these two triangles. It has not been asked from us in the statement, but I am writing it here, the load function. The load function is this one, k into x minus a power 1. Remember that this is for positive slope k. Here we have k1 into x minus 0 power 1 plus k2 into x minus L by 2 power 1. Because the first triangle, this triangle, the top triangle, has 0 distance from the left end. So A is 0 for this triangle. The second triangle has A equal to L by 2. So we have 0 and L by 2. K1 is 2 W naught by L and K2 is minus 4 W naught by L. So we have inserted the values here. This is load function. Remember that load function is written for distributed loads only. Either Uniform distribution or linear distribution or quadratic or whatever the distribution is. Next is shear force function. So remember that for shear force and bending moment, we will always start from the left end, and the load or moment at the left end is the initial condition. So here at the left end, V naught is equal to the concentrated force at this end. It is 1 over 4 W naught L. But there is no moment at the left end, so M naught is equal to 0. We will need these values in the next slide. We will write Vx minus V naught is equal to, now we will go to the table. Shear force for the distributed load is minus K by 2 x minus A power 2. So it will be minus K1 by 2 x minus 0 power 2 minus K2 by 2 x minus L by 2 power 2. For the upper load, A is equal to 0. For the bottom load, A is equal to L by 2. Okay. By putting the values of K1 and K2, x minus 0 means x, and x power 2 is x square. This term will simply become x square. K1 is equal to 2 W naught, this is here, 2 W naught over L, and K2 is equal to minus 4 W naught over L. So by putting it here, and after simplification, and V naught for us is 1 over 4 W naught L. So 1 over 4 W naught L with negative sign on this side will become positive on the other side. If you do not want to write V naught here, then you can simply keep the force at the left end. This force at the left end, A, RA, or this one. You can also write singularity function for this load, which will be singularity function for a concentrated load. It is here. For a downward concentrated load, it is minus P into x minus A power 0. For downward, it is minus P. For upward, it will be plus P. Singularity function for this load can be written as plus P, so plus 1 over 4 W naught L to x minus A power 0. A for this one is 0, distance from the left hand. So it becomes 1 over 4. X minus 0 means x. X power 0 is 1. So we can write singularity function of this load here. If we do not want to use this initial condition, so instead of that, we can consider the concentrated load or the reaction force at point A as a load, at a concentrated load, and we can write its singularity function here, which is this one. Similarly, for bending moment, mx minus m naught. So m naught is 0. There is no bending moment at the starting point, at the initial point left end. Then we have 3 loads. Which 3 loads? These 3 loads. This distributed load, the top distributed load, the bottom distributed load, and this concentrated load, RA. Remember that we will always ignore loads or moments at the rightmost end of a beam in the singularity functions method. So we will ignore the singularity functions caused by the load or moment existing at the rightmost end. In this case, it is RB. So we will ignore this RB. We will only consider this downward load with slope K1, this upward load with slope K2, and this upward concentrated load RA. Okay. For the for the distributed loads, we have bending moment function as minus k over 2 into 3 minus k over 6 into x minus a power 3. And for a concentrated load, it is minus p into x minus a power 1. This is for downward force. If we use upward force, in our case we have upward force, it will be plus p into x minus a power 1. Okay. The first one was minus k into x minus a power minus k over 6 into x minus a power 3. So we have minus k 1 over 6 into x minus a power 3. For k1 we have a equal to 0. Distance from the left hand is 0. X minus 0 power 3 minus k2 over 6 into x minus L by 2 power 3. For k2 we have a equal to L by 3. And the last one will be plus p into x minus a power 0. Okay. So by putting values of k1, k2 and p in this case is the upward load 1 over 4 W naught L. And this p has a distance of 0 from the left hand. So this term x minus 0 power 3 is simply x cube. Here also x minus 0 power 0 becomes 1. So the load p itself remains here. By putting values of k1, k2 and p, so we will get moment equal to this function. Now we have general expressions for moment and shear force. This was first part of the problem. You can also draw their expression, their curves if you have a graph paper. Now we will find values of, this was first part of the problem, to write equations for shear force and bending moment at any point. For the second part, we were asked to find bending moment and shear force at C, D and E. At C, x is equal to L by 2 here. At D, at this point, x is equal to L by 4, and at E, x is equal to L. So we will put x is equal to L by 2 for point C. If we put x is equal to L by 2 in this expression, the second term becomes 0 when x is equal to L by 2. So the second term becomes 0. This term will be 0 and all other terms are there. So VC becomes 0 and MC becomes 1 over 12 W naught L square. When x is equal to L by 4, again the second term, this term will be negative. When x is equal to L by 4, this term will be negative. Similarly, in the moment expression, this term will be negative. And if this term is negative, we will neglect this term for x is equal to L by 4. This term is negative and we will neglect this term. All the other terms are existing. Here VD and MD can be calculated. Similarly, when x is equal to 3 L by 4, for E point, I misquoted here. For E, x is equal to 3 L by 4. So by putting x equal to 3 L by 4, x equal to 3 L by 4, it is a positive term. This one also. For x equal to 3 L by 4, this will be a positive term. And if it is a positive term, it will be replaced with a regular parenthesis. This will be positive 1 over 4L, positive 1 over 4L. And after simplification, VE and ME can be calculated. This was asked in the statement of the problem.